So algebra is the area of mathematics. I wasn't sure where to start or what to cover. And so I thought I'd go ahead and create a set of lessons here for us to get started, and that we can move past some of this if it turns out to be too easy. But what I did was I picked a lesson where the problems get harder. Rate times time equals distance. I'm sure that this is something that all of you have covered before. But these are types of problems where the problem solving itself can get harder, and it's good practice for reading word problems and setting up equations, really all the way up to the highest levels. Those of you who plan to study physics, you will do more and more and more of this as you go. So let's go ahead and take a look at the lesson. As you can see, rate times time equals distance. What's another rate times time equation?
Distance equals, wait, what am I saying? Time equals rate, time equals distance over rate.
That's true. This is a good point. We can take a look at this equation, rate times time equals distance, and we can always rewrite it. And this is true for all of the types of formulas that you encounter in mathematics. You can look at them one way, but you could rearrange them. And really and truly what we have is an identity, meaning that both sides of the equation are always equal regardless of the values of the variables. So it's better to look at this as an identity than a formula, because we may need one piece of it rather than another. Okay. I was thinking of another possibility, which is rate times time equals work. And some of the problems that we'll tackle today are going to be work problems, not distance problems. Let's go ahead and start at the beginning. And let's work a few of these. And once we've worked a few of them, you all can tell me how close we are to a good level of discussion. First problem, how long measured in hours does it take Alyssa to ride her bicycle 30 miles if she rides at a constant rate of 10 miles an hour?
3 hours.
3 hours. Okay. And that was pretty immediate. So tell me, what did you do?
You basically divide the distance by the rate.
And we can solve and find that t equals 3 hours. Okay, good. How long measured in minutes does it take Alyssa to ride her bicycle 3 miles if she rides at a constant rate of 15 miles per hour?
minutes.
10 minutes.
12 minutes.
I got 12 minutes.
Oh, yeah, my bad, 12. Oh, my Lord.
Rate times time equals distance. And we can solve and find time is 1/5 of an hour, but we're asked about minutes, so we can multiply by 60 minutes per 1 hour, cancel out the units that we don't want, and we get 12 minutes. Okay, so far so good. The problems will get harder. If Mary takes 30 minutes to walk uphill 1 kilometer from her home to school, but it takes her only 10 minutes to walk from her school to home along the same route, what is her average speed in miles per hour for the round trip?
3 kilometers per hour.
Yeah.
No, it will be total distance over total time, which will give us the answer.
Okay.
Yeah, so it's 3 kilometers per hour.
Rate times time equals distance. We'll go ahead and say rate equals distance divided by time. And in this case, that distance is 1 plus 1 kilometers. And the time is
2 divided by 40.
and then we can multiply by
60.
and we get 3 kilometers per hour when we do. That was good. You all are very quick with the basics for sure. We will be able to focus our time on the hard problems when they come. One car left a city at 2 p.m. and traveled at an average speed of 40 miles per hour. A second car left at 4 p.m., traveled the same route, and overtook the first car at 9 p.m. What was the average speed in miles per hour of the second car?
56 miles per hour.
$56 miles per hour.
Okay, how do we work this one?
Okay, so we find out how much is the distance, what's the distance, and then the time for each car. For the first car has to cover 280 miles in 7 hours, and the second car has to cover 280 miles in 5 hours.
I'm leaving off the units this time. And of course, most of the time we should probably leave the units in to make sure that everything we're doing is fine. Here's another one. We'd say rate 1 times time 1 equals distance. Rate 2 times time 2 equals distance. What can we do with these two equations?
Subtract.
Possibly subtract, or we could we could say A equals B and B equals C. So A equals C. Transitivity.
Yeah.
And we don't even have to write those ratios. I just wanted to write, one possible problem-solving perspective, which is that we have, equal ratios. Okay. Let's jump a little further ahead. Now, we'll just keep going straight through. It won't take us much time. Let's make sure that we don't leave any possible tactics behind as they get harder.
Mr. Crawford, I think I have the answer.
What do you get?
I got 7 for the rates. 7 miles per hour.
How'd you do that?
So I made the rates a variable. So I said that one cyclist is traveling at r plus 4 miles per hour. Another cyclist is traveling r miles per hour. So I said that the rate at which the distance between them closes is equivalent to the total sum of their rates. So it's r plus into brackets r plus 4 miles per hour, which is 2r plus 4. And it said that they traveled for 45 minutes, which is equivalent to 3/4 of an hour. So, and that's supposed to give me 13.5. So from there, I just used deductive reasoning to find that 2r plus 4 equals 18. And so after I found out what the rate for them distance closing is, I just made s the subject, and that's how I got s to be 7. So r equals 7 miles per hour.
Okay. By the way, what you called deductive reasoning, tell me that part again.
So I written it out as an equation that 2r plus 4 times 3/4 of an hour, which is the 45 minutes, is equal to 13.5, which led me to, which I used reasoning to find out was 2r plus 4 equals 18.
Okay, so let's talk just a moment about terminology. First of all, I've written out the equations. We can start with an equation for each of the two cyclists, and because the times are the same, we can add them together, and that's when we find some of the information that we were given in the problem, and then we add the other information that we were given in the problem later on, and now we have a very simple system of equations that we can solve right here. And we can find that R1 equals 11 and R2 equals 7. So our answer is 7. You were correct. You said deductive reasoning, but deductive reasoning is usually where we eliminate logical possibilities as we go. Whereas here, I don't think that we are technically using deductive reasoning here, but not to say deductive reasoning isn't an important part of our tool set.
Okay, sorry.
Not a worry. Okay, let's take a look at number 6. Oops. There we go. What am I doing here?
You're
we
showing us the path of the race and dividing it into each of the intervals stated.
How can we think about this one?
they're showing us the information we know about each interval. The first, which was half, we know he ran for 3 minutes. The next one, we know he was going at a rate of 8 meters per hour, miles per hour. And finally, we know that his final rate in the last stretch of the race was 3/5 of his rate at the start of the race.
Good. So focusing on the problem, how can we think backward from what we're being asked to connect to how to, this is 3 different kinds of information that we're given in these intervals. So what do we do to connect ourselves to that question?
We
You
could
can
try
write
and
the
lay out the
information.
Go ahead, Non-Orly.
If you write the information, you'll be giving the question down and see how they relate to each other.
We're asked about the average speed. What should I write?
You can write the rate, the time, and the distance given for each of them in the question.
Well, before I write for each of them, I'm going to write the total here because we're trying to figure out the total rate. So total rate, total times total distance. Let's see, rate equals distance over time, and we know the total distance, 1 mile divided by time. What did we learn?
Can't we start by like finding the distance of R1? I mean the rate R1, because we know so that's half of the race, so that would be 0.5 miles.
Possibly, but before we decide exactly what we're going to do with the given information, if we think backward, that's what we're doing over here on the right. Now, this one's a harder problem than the previous ones. So I wanted to think backward. How does it help us to think backward? What information do we need to solve the problem?
The
the
time.
rate.
The time.
Or
Non-Orly is correct. We need the time, right? We wrote out rate times time equals distance. We isolated the rate as distance over time. And we said, well, we know the total distance. The total distance is 1 mile. And so we see that what we need is the time. That helps us. It helps us focus in on what it is we're trying to do with the given information. So now we focus in on the information we had at the beginning. We go, well, we do have the time of the first interval. That's given exactly as we wanted, 3 minutes. Now we can go to the next piece. The third quarter of the race was run at 8 miles per hour. What do we do with that?
You find how long it took to run quarter a mile.
Okay. How long does it take to run a quarter of a mile if you're running at 8 miles per hour?
1 out of 32 hours, 1/32 second of an hour, which
1/32 of an hour. I'll just go ahead and write it down that way. Okay, good. Now, how about the last part?
One 24th of an hour.
How do we get 1/24 of an hour?
by finding the
Well,
rate for the half of the journey.
Okay, so what was our rate during the first half of the race? Took 3 minutes
10 miles per
half a
hour.
mile.
Is it 10 miles per hour?
Yeah. We go for a tenth of an hour, we run a mile. So we have 10 miles per hour as our rate. So we have 3/5 of that, 6 miles per hour. And if we're going at 6 miles per hour, then yes, it takes 1/24 of an hour to go 1/4 of a mile. Okay, what do we do with our information?
We can now find the time to find the rate. So we can add the times we have.
I'm going to change all these. The first one's given as minutes. I'll call it 1/20th of an hour after we convert. And now we need to add these funky fractions. What's our common denominator?
480.
It could be
Okay. That is the fraction of an hour it took to run the mile. So now what do we do?
You put the value of the time in the formula. So you get 1 mile divided by 59 over 480.
Okay, and it asks us to express our answer as a decimal to the nearest tenth. What do we do with 480 over 59 now?
You divide.
You divide.
And well,
What do we get?
8.1.
8.13. 8.135.
Okay. So what did we do that helped us with this problem? What are all the things that we did that helped us?
We changed the subject of the formula we were given.
Anyone else?
Adding all the data we were given the question to come up with a solution.
So I would say the important things were we drew a picture. We drew a picture and chopped up the information into pieces. Then we looked at what we wanted to answer, and we worked backward. Once we worked backward, it was far easier to understand how exactly we wanted to convert the information that we had into the information that we needed. And then solving the problem was just a matter of arithmetic. Okay, let's take a look at number 7. Maria normally spends a half hour driving to work. When her average speed is 10 miles per hour slower than usual, the trip takes 10 minutes longer. How many miles does she drive to work?
Well, we can start off by looking at the middle sentence. When her average speed is 10 miles slower than her usual, the trip takes 10 minutes longer. We could figure out where that would be.
What should we write down? Do we have any equations to work with?
Yes, RT is equal to D. And
Okay, let's say that R and T are her usual rate and time. What else?
R is equal to D over T.
Maybe we do that. I don't want to do that just yet. I would like to
R minus 10.
I would like to avoid fractions where at all possible. The more we multiply and the less we divide, the easier life is. Sorry, Snake, what was that?
I said R minus 10 times T would be equal to D.
Okay. So when her average speed is 10 miles an hour slower, the trip takes 10 minutes longer. What should my second factor be here? T plus...
T plus 10.
I could do T plus 10, but I would rather do T plus 1/6. Why is that?
Because 10
10
minutes is 1/6
of
of
an
an hour.
hour.
Yeah, I'd like to express all the units the same as we go through the two equations. And so if we're thinking in terms of miles and miles per hour, and we were thinking in terms of miles per hour, well, either we want to think all in minutes or all in hours, one or the other. But I think it's going to be easier to translate everything into miles and hours. So we have these two equations. What can we do with them?
This equation is for when she only drives slowly, but so we can find her normal rate when she's driving.
Can you repeat that for me, Non-Norley? Tell me what to do just with the equations.
You can write another equation for how she drives normally, because this one is for when she drives slowly.
Oh, but we already have that equation. That's just R times T equals D. That's the normal equation. And I didn't write this down. We could have, at the beginning, it's generally good to write down the definitions of your variables.
Mr. Crawford?
Yes.
Shouldn't it be 1/3 instead of 1/6? Because it took 10 minutes longer. She drove for 30. It takes 30 minutes normally. So shouldn't it be 1/3?
Okay. So what you're saying is that we can plug in that that information about how long it takes her to drive to work. Okay.
Yep.
So Maria normally spends a half hour driving to work. So that's T. And then we have R minus 10 times 1/2 plus 1/6. Okay.
But Mr. Crawford, I'm kind of confused because shouldn't the 1/6 be at 1/3 because it's 10 minutes longer and she's driving for 30 minutes?
It normally takes her 30 minutes, which is 1/2 hour. So this right here is a normal day. However, this time she drove slower and it took 10 minutes longer, which is 40 minutes, which is 2/3 of an hour. Am I misreading something?
So we're basing everything around the 60 minutes, not the 30 minutes.
Wait, so how did you get the 1/6?
Because 10
1
minutes,
10 of an
1 out of 6 of an hour.
Wait, we have look at
Okay, yeah. Thank you.
have information in hours and we have information in minutes. And it's probably best before doing our calculations to just go ahead and convert everything to 1 unit.
Yeah, I got that. Yeah, thank you.
The hours. And so the 30 minutes winds up being 1/2 hour. And then the 10 minutes longer is an hour plus 1/6 of an hour, or 40 minutes, which winds up being 2/3 of an hour. Are we all on the same page? Do my equations look right?
yes.
Okay, what can we do with these equations?
We could multiply them out, and then we simplified.
We can multiply them out. I always like to save computation until I have to do it, or I need to do it, or it's advantageous. Before we multiply anything out, what can we do?
Since they both equal d, you can make them equal each other.
Good. The left-hand sides both equal d, and we can just equate them directly to each other. I'm moving the factors in front just because I usually keep my factors, my constant factors in front that way. And now we have an equation we can solve. Before I solve it, I'm going to go ahead and get rid of the fractions. Even when you are very experienced, fractions are still one of the ickiest things to deal with in mathematics. Okay, so now what?
Since we found the rate, we can find the distance because we already know the time.
Good. We're asked for the total distance, and probably the easiest place to plug in is this equation right here. And we wind up with d equals 20 miles. Any questions or thoughts about this one? Okay. Make sure that you justify all the units to the same unit, and it'll make life easy if you do that from the start. And now we have one about Wendy. Wendy ran from home to school at a constant rate of 8 miles an hour. Then she ran back home at a constant rate of 6 miles an hour. What was Wendy's average rate for the trip?
I think we'd add and divide by 2, but I'm not sure.
Okay, so let's keep that as a conjecture. Do you guys know what a conjecture is?
Not really.
No.
Isn't it like a factual statement that you can make about a problem that helps you with solving other problems?
Let's just call it like a guess. In science, we call it a hypothesis when we have a guess as to whether something is true, and then we test the hypothesis to see if the theory continues to hold. In mathematics, we make a conjecture when we have a guess, and then we try to prove that conjecture to see if it holds. So we're going to hold this on the side, and we will find out if it's true, but we're still going to work the problem rigorously to see if it's true.
I had an idea.
What's your idea?
So we could try to find the time, like an equation for time. So the time is the distance over the rate. So d over 8.
Okay, so rate times time equals distance. And you're saying that time is distance over rate. How? Okay, I see what you're doing. We have a constant distance between both trips. So you are using the fact that distance and rate are, well, rates are given, but the distance is the same. You know what? I don't know if I like this. I think I want to keep RT equals D. If I don't have to make fractions, I don't want to make them. But in particular, what's true about these two trips? We have a rate for each of them.
And it's the same
They
distance.
It's the same distance, right? So with these two equations, we have 8 miles per hour times time 1 equals distance, and that's equal to 6 miles per 1 hour times second amount of time. Okay, what do we learn from this?
We can equate
We
both
have
equations
to.
to each other.
Okay, we can equate the far left and the far right. And what do we find?
The time.
Do we know the time?
No.
We don't know the time, but we know a relationship of the times. And here's the
Yeah.
thing. We were never going to know the amount of time in this problem. We were never going to know because we don't have that information. We don't know the distance from school to home. It could be any distance. We're going to solve this problem without ever knowing what that distance is and without ever knowing what the time is. Let's see how. Okay, we want to know Wendy's average rate for the trip. And someone mentioned manipulating the original equation earlier, and maybe I should have listened. That is what we need to do for the final calculation. So rate is distance over time. For us, I'm going to call the distance little d here so that we don't confuse it with big D. What is our total distance for the two trips?
T1 plus T2. Sorry, not T1 plus T2.
2D.
2D. And what's our total time?
T1 plus T2.
T1 plus T2.
Okay. And how can we write that?
3/4 of T1 plus of T2 plus T2 dividing 2D.
Okay. Now what? What's D over T2?
The rate. No.
Do we see D1 and T2 together anywhere?
Yes.
Where do we?
The 2D divided by 3 over 4 T2 plus T2.
Well, we need it right here. What is D over T2? Look through our original information.
It's the rate.
Which is?
6 miles.
Yeah, it's right here. If we divide that equation by T2, we get the rate in which she ran the back home trip. So our answer is 8 times 6 over 7, which is 48 sevenths. And if we wanted, we could write that as 6 and 6/7. So does that fit our original conjecture?
Yes.
What's the arithmetic mean of 8 and 6?
7.
7.
7. But our answer was 6 and 6/7.
Yeah, so that's wrong.
So the
Our
conjecture
conjecture
failed.
was proven wrong.
So we proved the conjecture wrong. On the other hand, is there a formula now?
Yes.
Maybe it's yeah, because it's 8 times 6 over the all over the arithmetic mean.
Okay, let's make sure that we know where those numbers are coming from. That sounds reasonable, but let's make sure that we know. So our numbers, I'm going to start right here, where we had 2 times the distance over time 1 and time 2. And time 1 was really D over 8. Right, we got those equations from the middle of the board that we can use. The second time was D over 6. And we can divide the distance, D, out of the numerator and the denominator, and then we get 2 over 1/8 plus 1/6. And if we multiply the numerator and denominator by both 8 and 6, we get 2 times 8 times 6 over 8 plus 6. And there are different ways to write this. Now, here's what I'm going to point out is we can conjure a general formula. If we have 2 rates, and I'll just call them A and B. If A and B are our 2 rates, then we have 2 times A times B over A plus B. And sometimes we might see that expressed as 2 over 1 over A plus 1 over B, which is the reciprocal of the average of the reciprocals. Does anyone know what that's called?
Harmonic mean.
Good. This is the harmonic mean of the 2 rates. And for those of you who study physics long enough, you will wind up seeing that harmonic mean again and again and again as you work problems that involve rates within physics. But if you want, you can just remember it this way. And we have a nice little formula. If you don't have a formula, you can always solve the problem, figure it out again. but it's nice to see that. If you get used to where it is harmonic means show up, then you may learn to solve problems like this a little bit more quickly. So somebody give me an intuitive explanation. Why doesn't the answer wind up being just the straight out arithmetic averages?
Because you have to
Because
divide by their reciprocals.
Okay, I'm looking for an intuitive explanation though, right? That tells us what we do in the mathematics. But from the beginning, why would we maybe say, hey, we shouldn't take the averages of 8 and 6. They're not things that are going to fit together in an average sort of way.
I think because the time for both of them would be different. For example, since the rate is equal to distance over time, but for both of the, and you can only find the proper arithmetic mean if both of the times are the same. And so it wouldn't work in that way.
Good, right. We spend more time, or she spent more time running 6 miles per hour than she spent running at 8 miles per hour. And so the 6 miles an hour winds up weighting in more. And so we wind up being closer to 6 miles an hour. And in fact, we wind up with a 6 to 8 ratio along that interval if we look and see how it is we're actually weighting these together. All right, any questions or thoughts about this?
Can you
Okay.
please go over the harmonic mean again?
Sure. Like what is the harmonic mean, or how it is that we got the formula?
How you worked it out.
Okay. So in the end, we wanted distance divided by, we want the rate, which was distance divided by time right here. And so we split the time into the two different times of the run. T1 being the amount of time she spent running 8 miles an hour. T2 being the amount of time she spent running at 6 miles per hour. And so we took that T1 and T2 and we went back to these equations, the equation for each leg of the run. And we said, well, we can replace T1, we can substitute for T1 and we can substitute for T2, both in terms of D, which is nice because we have D in our numerator, right? So we substituted for these. And if you follow the green arrow, we got that equation. And then we divided D out of the numerator and denominator. And that's how we wound up with this computation right here. And if it were rates of A and B instead of 8 and 6, we would walk through all the same calculations, just replacing all the 8s with A and all the B's with 6. And then we would have a general derivation of this formula. And if you've never derived a formula like this before, go ahead and do that on paper. Everything's going to look the same up here, except that you're going to have, your 8s will be A's and your 6s will be B's. Try to write that out yourself. Also, try to teach a friend. That's a great way to learn mathematics and know that you have it down solid, is if you can write your equations out nicely enough that someone else who hasn't seen this before can understand you, then you know that you really get it. Okay, moving on. So I'm just going to point out that I've left you with solutions to all the problems that we just walked through and kind of a summary of the different principles and tactics. It's good to take a look over that. We've got this formula that we developed at the end. And then I've got some challenging problems. Like the last few problems that we worked, These are not simple, they're not easy. And what I'm going to encourage is for you to work as many of these as you can as homework. And if you have questions about any of them, post them on the message board. They get pretty tough at the end. And I might answer a few of those. I've got answers and solutions to a couple, but not solutions to all of them, so as not to guide you too far yet. So now we're going to spend the second half of class talking about a fun topic. Are you familiar with the term figurate number?
No, please.
No.
So you're familiar with
No.
triangular numbers and square numbers, right?
Yes.
Yes.
Yeah.
So all of these types of numbers and more are called figurate numbers. And we're going to take a look at some of them. But first, let's start with just a definition of what is a triangular number. And some people arrange the dots, in a more equilateral type of form. But these are triangular numbers, and they go 1, 3, 6, 10. And then we've got square numbers, like in the bottom left-hand corner. And they go 1, and then we add 3 dots. Actually, let's do this. 1, add 3 dots to get to 4. Add 5 dots, and we get up to 9. Add 7 dots, and we get up to 16. Then I'll use green again. Add 9 dots, and we get up to 25. Does anyone know which ancient civilization, at least as far as we know, came up with these figurate numbers? So it turns out in Egypt. In Egypt,
I almost said it.
Almost said it. In ancient Egypt, they had some playful mathematics. And one of the reasons was they didn't have a conception of area. But they were farmers, right? They had to grow a whole bunch of wheat around the Nile River and collect that wheat in order to feed civilization. So instead of having a concept of area, they counted up dots in patterns to compare quantities of grain that they would grow. So it's kind of an interesting little tidbit. If you don't have one concept, you might be able to use another to replace it, to make use of it. Okay, so now other shapes. We have triangular numbers, we have square numbers, and you may have seen one or both of those before, but we can make pentagonal or hexagonal or heptagonal numbers. And this,
How?
yes?
You were saying we could make octagonal numbers, and I was like, how?
Yeah, we can make any number of sides that we want, and the idea is that we focus on building from a corner, and we go out from that corner in 2 directions. And so all of the polygons of the same shape, like the hexagons, or sorry, the pentagons that I'm working with here, they have the same shape. We're sort of emanating from that point, and all of them share 2 sides. And then we can count up how many dots we wind up with, and we can compute the first few of each type of these numbers. So we've got triangular numbers, 1, 3, 6, 10. Help me fill out this grid. What comes after 10?
15. 21. 28.
28.
30.
37.
36, sorry.
And so going from one to another, we add 1 to 0 to get the first triangular number. Then we add 2 to 1 to get 3. Then we add 3 to get 6. We add 4 to get 10. We add 5 to get 5. So we see that this is the differences are arithmetic. Right? The sequence itself is not arithmetic. We don't have a constant difference, but the differences have constant differences. Okay? Is that going to be true for all of these, or is that just triangular numbers?
I think for all of them.
All of them.
Why would that be the case?
Because square numbers, it's increasing in twos. The differences increases in twos.
Okay.
Sure.
How do you know for sure?
Isn't that how it works with quadratic sequence? They have a second difference that you need to find out in order to solve those sequences.
That's true, Salorm. Can we prove that?
I'm sorry, I didn't quite catch what Salorm said. Could you repeat, please?
Sure. He's saying that if you have any sequence that is generated by a quadratic function, and I'll write an example down. Our example could just be f of n equals n squared. That gives us the nth square number, right? And if you took f of n plus 1 and subtracted f of n, we'd wind up with n plus 1 squared minus n squared, which is 2n plus 1. And 2n plus 1 is linear. That's where we're going to get arithmetic differences. We get the sequence 1, 3, 5, 7, 9.
Okay, thank you.
Oh, you're welcome. You know what? I should make a bigger lesson out of this piece. So in mathematics, there's something called discrete calculus or difference equations. And this is good to see now, because later on when you do calculus, you're going to start out thinking the same way, but instead of subtracting, like moving one unit at a time to go from one term to another in a sequence, you're going to go tiny, tiny intervals at a time and imagine what happens as that interval approaches 0. So that's why we sometimes call this discrete calculus. So I'm going to write the sequence of pentagonal numbers up here. Okay, I think I have these right. So let's take a look at the row of differences. And you may see this triangle or delta symbol used when we write differences. 4, 7, 10, 13, 16, 19, 22. And then if we write the differences of those, we get 3, 3, 3, 3, 3, 3. Now let's see what happens with just some quadratic function. Let's say that we have f of n equals 2n squared minus 3n plus 5. And now let's write the first row is just going to be our function row. And somebody tell me, what is f of 1?
Four.
Okay. What's f of 2?
7.
What's f of 3?
10.
It's not 10. Somebody plug 3 into that formula for me.
$14.
Okay, what's f of 4?
25.
F of 5?
40.
Okay, I hope I've computed those all correctly. And now let's take a look at the differences. Seven minus 4 is 3. 14 minus 7 is 7. 25 minus 14 is 11. 40 minus 25 is 15. 19, 23, 27. And now let's look at the second order differences. 4, 4, 4, 4, 4, 4. We have a constant row. And Salorum claims that it's necessarily true that we have a constant row there. So let's take a look in general. So we have the conjecture of Salorum. In general, let's say f of n is equal to a n squared plus bn plus c. And the first difference we might define as f of n plus 1 minus f of n. And everybody give this a try on your own paper. See if you can walk through this accurately.
Mr. Crawford, doesn't
Yes.
that result in a constant difference of 1?
Can you repeat the
Because-
question?
Doesn't it result in a constant difference of 1? Because say if n is 5, it's 6, and if minus 5, which is 1, so wouldn't that be a constant difference of 1? No matter, because n has to always be the same.
Let's see. We'll find out. So this is our first difference. And now we're going to define our second difference. As such. Same definition. It's kind of like a composite function. We're just applying the same definition again, a second time. What do we get?
Two a into bracket n plus 1 minus 2an.
What's that equal to?
A.
It's equal to 2a. That's it. So we have demonstrated that Salorm's conjecture is true. We just have a constant here, and it's equal to 2 times the lead coefficient of the original quadratic. So, but it was not equal to 1. It was 2 times the original lead coefficient. But it is a constant series. If you start with a quadratic sequence, like this one right here, and perform 2 sets of different calculations between the terms, always subtracting right minus left. It's not just the total distance between the two. It's not going to be an absolute value. It's right term minus left term. So remember that if you have a sequence that goes up and down a little bit. But yeah, we wind up with a constant term on the second difference. And if you have a polynomial that is a third degree polynomial, here's the thing, every difference will reduce the degree of the polynomial by 1. So the differences of cubic sequences will be quadratic. The difference between quadratic sequences, the difference between the consecutive terms, will make an arithmetic sequence. And the difference between the terms of an arithmetic sequence make a constant sequence. So this is good to know. It's handy for a lot of explorations. It's handy for figure-it numbers. And most of the figure-it numbers that we deal with are two-dimensional, and they wind up being quadratic in nature. Of course, we haven't proved that yet. We haven't shown that these figure-it numbers are quadratic in nature. So let's do, maybe we'll come back and fill out more of this table. Let's see, do I have, okay, good. I have pictures for this. So let's see what happens as we build larger. You know what these are? Those are the differences. That's delta. That is one triangular number minus the previous triangular number is whatever we added to the previous triangular number to get the new one. Okay, in the case of triangular numbers, the differences are linear. They are an arithmetic sequence. For square numbers, we can see, okay, we add these two sides. We add a side and we add a side, but that's too many, so we subtract one. Okay. So if we were going to, from n to n plus 1, we added 2 times n plus 1, but then we subtracted 1 because we were overcounting. This is correction for overcounting, or principle of inclusion-exclusion. Add a side, subtract the pieces at the corner that we added more than once. So if you've ever noticed that the differences between consecutive square numbers form all the odd numbers, this is why. Or this is one reason that we can tell why that's true. But let's look at the pentagonal numbers because that's where it gets a little harder. If we have a previous pentagonal number and we add these pieces to the sides, we're adding 5, 5, 5. But oops, we added that corner twice and we added that corner twice. So what we added was 3 times 5 minus 2. And each of our differences looks that way. 3 times the new side length minus 2, because those 3 sides intersect in 2 vertices of the pentagon.
So 3n minus 2.
3n minus 2. That's when you're going from n minus 1 to n. Or you could say 3n plus 1 if you're going from n to n plus 1. And we can see I've got some difference tables here down at the bottom of the page. So here I've got a more filled out table here. And let's see how we can make use of this table. We're kind of getting a grip on what's going on. We're seeing the process better and better. Let's fill out some more terms. Let's fill out the rest of the triangular numbers on the top row. What's the 9th triangular number?
45.
Okay. Somebody else give me the 10th.
55.
55. Then the 11th.
66.
66.
And the 12th.
78.
Now the square numbers are the easiest to compute. And let's look at these for a moment. So we've gotten a grip on the pattern going from left to right, the pattern across each row. Those are linear patterns. So let's talk about pentagonal numbers. That linear pattern, we go up 1 to get to 1, up 4 to get to 5, up 7 to get to 12, up 10, up 13, up 16, up 19, up 22. What's next?
25.
25. So what's 92 plus 25?
117.
117.
Good. Now how much do we add?
28.
28. What's 117 plus 28?
145.
145.
What's 145 plus, what do we add?
31.
31.
31.
176.
And what's the very last one, the 12th one?
200.
209.
I think we get 210.
210.
Okay. Hexagonal numbers. I'm not going to do any of this one for you. Just tell me the numbers.
You add 33, so 153. $190. 230.
Wait, I don't know if that one's correct.
Yeah, I made a
It's
mistake on that
231.
one. Sorry. $276.
Okay. And here I want to point something out. Let's say that you want to know the non-agonal numbers. And you might think, well, gosh, drawing out all those little dots is going to take forever, right? So what can we do to kind of get started without having to worry too much?
Well, we can tell based on the other numbers that the second term in the non-agonal numbers is going to be 9.
Okay, good. So we have two terms.
And if we try and find a pattern in the third set of terms, we also find out it's a difference of 3. So the next one's going to be 24 for non-agonal numbers. And now that we have at least 3 sets of numbers, we can find out the second difference and use that to start computing differences.
Yeah, we already had enough, actually. We know that the first difference, you know, we can really always say that we're starting at 0. There's like an implicit 0 before all of these. The 0th triangular number is 0. The 0th square number is 0. The 0th non-agonal number is 0. And now we already have 2 differences on the first row of differences, which means that we have the second difference, the second order difference is 7, 8 minus 1. And so if we add 7 to 8, we get 15. So 15 is what we add to 9 to get 24. And then we add 7 to 15 to get that next difference, which is 22. So the fact that we already know that 2 differences down, we have a constant, that's enough to build. Let's see that in action. Non-agonal numbers. First difference is 1 and 8, and then the second difference, 7. Well, 7 has to be constant. So we add 7 to 8 to get 15, and then we add 15 to 9 to get 24. And that is our third non-agonal number. And then we start building at the bottom again because we know those differences are constant. 7 is the difference between 15 and 22, and then 22 is the difference between 24 and 46. So 46 is the fourth non-agonal number. Good. We don't actually have to do all that much work. Well, it's still a little bit of work. What would we like to have? What if we wanted to know the 50th non-agonal number? Should I do this 50 times over?
Well, Mr. Crawford, you said you were asking how would you do this if you were giving like the 50th term?
If we wanted the 50th term.
Well, the basic, well, it's a quadratic sequence, so we know that the nth term will come in the form of a(n) squared plus bn plus c.
Okay. So if we say f of n is a n squared plus bn plus c, now we can get equations by doing what?
By making n the 50.
Well, before we do that,
We need to find a, b, and c.
we need to find a, b, and c. And we can just plug in a few simple values. Let's see what these equations look like. The first one just turns into 0 equals c. The second one turns into 1 equals a plus b plus c. And the third one, f of 2, is 9. So that's 4a plus 2b plus c. And now we have a relatively simple system of equations to solve. Let's see. We subtract these two, we get a plus b equals 1. If we subtract these two, we get 2a plus b equals 8. And then we subtract those two and we get a equals 7.
Shouldn't it really be 3a?
Yeah, sorry about that. Huh. Okay. So I don't think this is right. I feel like I must have made a mistake somewhere, but maybe I'm wrong. Oh no, this is right. I was comparing to the wrong formula for a moment. Okay, but I believe this is going to be correct. And if we want, we could write this as n times 7n minus 5, all divided by 2. That's one way to write it. But yeah, we can work this out if we want by computing a few terms. So this isn't the only way to work this out. We could also work it out like this. Let's say that we think of it this way. f of n is equal to, well, I'm going to name the functions I'm going to name the first difference function as g. And then finally, I'm going to call the last one c of n, call that constant function. Actually, let's do f of n, d of n for difference function, and c of n for constant function, since we're only going 2 rows deep. So f of n, well, maybe we start at f of 0. And we add f1 minus f0. What would that give us? If we add f0 plus f1 minus f0.
It would be f0 plus f1, and because we determined the f0 is c, and the only way for c to equal 0 is if c is 0.
Okay, you know, I'm gonna move forward and do this in a different way. It's kind of a different lesson and come back to this. Does anybody know a formula for the sum of the first n counting numbers?
With
just n?
With differences of 1, or
Suppose we wanted 1 plus 2 plus 3 all the way up to n. What's that equal to?
I had this.
N, n as in the number of terms. Since it's a simple list, it would be n terms over 2 multiplied against the sum of the first term in the sequence and the final term in the sequence.
Okay, let's talk about a second way to form this. Now I'm going to rewrite this as the sum as k goes from 1 to n of k. Is this notation that you're familiar with?
No.
Okay.
Yeah.
You will become familiar with it over time if you're not already familiar with it. That big giant letter that looks like a big E, a funky E, that's capital sigma. This is a Greek letter. And the number below, where it says k equals 1, that gives us a starting point for the variable k. And so sigma is for sums. So we're adding values of k from k equals 1 to n. So we call k our index variable.
So it's basically a notation form for the simple list that we have.
So you say simple list. A simple list is usually, just terms separated by commas.
Yeah.
It's for a series. Sigma is for a series. So we plug in 1, 2, 3, 4, 5, 6 for k, all the way up to n. And let's just do a couple of examples of this. If I asked, what is the sum as k goes from 1 to 5 of k squared? What would that be?
One plus 2 plus 3 plus 4 plus 5 all the way to k squared.
So we're not adding 1, 2, 3, 4, and 5. We're adding 1 squared plus 2 squared. That k squared that follows the sigma, think of it like a function. We're just plugging in for values of k from 1 to 5. And what do we get?
$55.
Good. Now we're going to use this notation to simplify our algebra. We're also going to use a technique called telescoping. Have any of you ever seen a telescoping series before?
No.
Okay.
No.
We're going to add one more piece to this lesson then. So I want you all to find the sum of this infinite series. It is not geometric. We're going to have to think of it differently. And I'll give you all a couple of minutes to work on this while I refresh my coffee, and then I'll come back and we'll discuss it. So I'm computing some partial sums right here, but I'm kind of getting tired of writing out all the fractions. So I'll just write the last one plus the next term. What's going on here?
The numerator is the denominator of the previous sum, and the denominator is the numerator plus 1.
Huh. So what's going to happen if we just keep going off to infinity?
Never get to 1.
It looks like we're getting closer and closer to 1. 1 minus a half, 1 minus a third, 1 minus a fourth. We're getting 1 minus a tinier and tinier fraction.
Mr. Crawford, didn't you say that this was, I think it was converging series?
It looks like a converging series. That's certainly what it looks like. And if we take S6 minus S5, well, that's kind of like the differences that we've been dealing with, right? The
Yes.
first order differences, well, we know what that difference is because it's whatever last term that we added, right? The sixth partial sum minus the fifth partial sum should just be the sixth term, which is going to be 1 over 42. But look, we can write that differently. We get 1 minus 1/7 minus 1 minus 1/6. And the ones cancel out, don't they? This is just 1/6 minus 1/7. Huh. 1/6 minus 1/7. Well, what if we wrote all the terms that way? By the way, if you notice, the terms are 1 over 1 times 2, 1 over 2 times 3, 1 over 3 times 4, 1 over 4 times 5. But now we have a way of rewriting these. We can rewrite the first one as 1 over 1 minus 1 over 2. And the second one is 1 over 2 minus 1 over 3. And the third one is 1 over 3 minus 1 over 4. What's going to happen as we go to infinity?
Infinity minus infinity minus 1 minus infinity.
If we reorganize the terms, we see that every term except the first pairs off with another term so that they equal 0, and the whole sum just equals 1. Everything else, it telescopes until we're left with just some simple term or maybe a few terms, and that's it.
Mr. Crawford, could we have also done it the way we did in a previous question, where we added a common value to each term and then canceled out?
Can you explain which problem?
In a previous lesson, when we were working with series, you showed us one way of going about it was adding a common value like 1, or you add the difference and then you work, and after you add the difference, you cancel out the other terms and you find out what's left is what's left is the first term and then another term that, so your n plus 1 term, and you worked it out, you sum them.
I don't think that, so you're talking about when we were doing arithmetic series, there's not a completely direct analogy, but some elements are the same. Don't worry too much about, how perfectly these two methods match up, right? There are going to be some elements that are the same in terms of, oh, look, we have a first term that's remaining. But the process is a little bit different for each. With geometric series, we gave the series a name, we multiplied by the common ratio, then we subtracted, and we did have, matching pairs of terms that disappeared, right? That part is the same, but here, here it's a different set of steps to get to the reorganization part. We take each term, which like the general term we might have written as 1 over n times n plus 1. And ultimately, we rewrote the general term as 1 over n minus 1 over n plus 1. Right? And we didn't even have to be good at rewriting fractions like this, because what we did was we took a look at the partial sums and we expressed the partial sums as some difference, like they're approaching 1. So we expressed each as 1 minus whatever that distance was that we needed to get to 1. And that allowed us to come up with a new formulation for each term. And sometimes you can come up with the formulation with or without the partial sums. But one way or another, once we'd rewritten the terms, we could regroup them in such a way that they telescoped. And everything from there was simple. Would you all like to see one more example of this?
Sure.
Yes.
Suppose we have the series 1 over 1 plus the square root of 2 plus 1 over the square root of 2 plus the square root of 3 plus 1 over the square root of 3 plus the square root of 4, so on and so on up to, this one's not going to go to infinity. I'm going to take this one up to 2020, root 2020, and root 2021.
Well, you could pick a few terms out and just, if you know their square roots, you simplify them to help make maybe the actual sound easier.
Maybe. What's another way we could write this? I mean, this is ugly, right? We have square roots added together in the denominator. We don't like that. It's not the way we usually communicate fractions.
You could write it in decimals or in indices form.
In what form?
Indices.
In decimal form?
No, you could write the square root in indices form or decimal form.
Well, I don't want to convert irrational numbers to decimal form.
You could multiply both. You could multiply the numerator and denominator by the square root. So it'd be root 5 6 plus root 6. Root 5 plus root 6.
Yeah, you multiply by the conjugate.
Yeah, here's what I call this: cleverly multiplying by 1. I think we've talked about this once before.
Yeah.
If we multiply
Yeah.
Salorm by 1, we still get Salorm. If we multiply Shreya by 1, we still get Shreya. Multiplying by 1 doesn't hurt. It doesn't change what we're working with. And in particular, a plus b times a minus b is what? What is that equal to?
A squared plus B squared plus 2AB.
Oh, no, it's not a plus b times a plus b. A times A is A squared. B times A is BA, or AB. A times negative B is minus AB. And then B times negative B is minus B squared.
A squared minus B squared.
A squared minus B squared. This is a difference of squares factorization. And in particular, that's what we're going to get in the denominator right here. Our numerator is just going to be root 6 minus root 5. But then in the denominator, we're going to get the square root of 6 squared minus the square root of 5 squared. Oh, look, we're doing exactly what we need to do to get those ugly looking numbers looking pretty. Now we're just dealing with integers in our denominator. And the whole thing simplifies to what?
Root 6.
The normal numbers, the original numbers.
The original numbers, but subtracted. How does that help us?
It helps us to convert all the other numbers into these forms.
Why does that matter?
It helps us to compute the differences between them easier.
Maybe. Still looks pretty ugly to me. I mean, does anybody know what the decimal approximation is for the square root of 2021? I can do the square root of 2 pretty well. It's 1.41422135, but I've seen that a few times before. Most of these are going to be a headache. We still need to do something good here.
You can multiply by the conjugates again.
Or we could square all. No, that wouldn't work.
All the transformation we need is done. We just need to organize.
Oh, we could name the beast and reverse. Like, I forgot.
We don't need to do that either.
And they cancel out because
Yes.
negative 2 square and 2 square, sorry, the negative root 2 cancel root 2. Then negative root 3 and root 3, negative root 4 and root 4.
Nicely.
They will all definitely cancel out, so you'll be left with -1.
Now, there's something that doesn't cancel out at the very end. You know, be careful.
2021.
Yeah.
Right. So cancel, 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 cancel. And in the end, the whole thing equals root 2021 minus 1. And that's it. Everything else just telescopes up and we get a nice compact answer. So these are some examples of telescoping series. And here's what I want you to see is that we can use the same telescoping method on things that we didn't realize that we might use it on. And here's an example. If I write n squared as a sum of differences, a sum of changes, I could write it as 0 squared plus 1 squared minus 0 squared plus 2 squared minus 1 squared Does everybody see that those are the same?
Yeah.
Okay. So on the left-hand side, we have n squared. And on the right-hand side, well, let's see, what are these terms? Well, it's 0 plus 1 plus 3 plus 5. Maybe I'll just forget about that initial 0. So the sum of the first n odd positive integers equals n squared. Hey, that's kind of cool. Okay, well now n squared then is equal to the sum as k goes from 1 to n of 2k minus 1. Well, that's the same thing as saying the sum as k goes from 1 to n of 2n, and then subtracting away all the ones separately. And then we can factor out a 2. And we can note that summing n ones together is just n. Now let's rearrange this equation. Let's add n to both sides. Oops. Pardon. And now we divide both sides by. And now we see that same formula that we came up with at the beginning. If we want, we can factor it and rewrite it, but this is the sum of the first n counting numbers. Any questions or thoughts on this? Oops.
Mr. Crawford, did you have just gone straight after finding the differences? Couldn't you have just said, well, the formula for this is similar to that of the counting numbers, and then you would have, because it's 1 plus 3 plus 5, and the difference for all of them is 2. So 2 and
We could have done this in a number of different ways, but what I wanted to do was to establish, I wanted to establish the methodology. I wanted to establish the fact that we could rewrite a polynomial expression as a sum of a first term plus differences that telescope. And you'll see why it is that we wanted to do that, because this is going to help us with harder problems, right? But I just want to show real quickly, right here, if you haven't dealt with sigma notation before, what's going on there, take a second look. is that in the sigma notation, we separate out 2 times each k from the ones.
In the way I see is that
Hold on,
sigma can be
Salorm, let me finish
like a
first, please.
variable.
Salorm, let me finish this first, please.
Okay.
So if we match these up, this is that line right there. And then we turned it into this, which is that line right there. We took one summation and we broke it up into 2. And then, we summed up one of those series right there, but we had the other one remaining right there. And that was, this is what it is that we wanted to compute. And then we just solved it like an equation right here. And so we're at the end of our 2 hours. So I want to go ahead and jump forward. Sorry that we're a little bit short on time. I just want to show you that we can use this to come up with other sums of polynomial series. And let's try to do this quickly. It may be something that you have to look back at, but maybe you can also apply it to coming up with formulas for figure-eight numbers, because every single one of those figure-eight numbers does have a formula that you can discover. So let's say that we want to know the sum of the squares of the first n positive integers. Okay, I'm going to write that as this sigma k squared, as k goes from 1 to n. So I'm thinking about the sum of squares, and I'm thinking about what we did last time, which was we rewrote squares as differences of first powers in order to find the sum of first powers. So I want to look at third powers. N cubed minus n minus 1 cubed is equal to n cubed minus n cubed minus 3n squared plus 3n minus 1, which is 3n squared minus 3n plus 1, right? And this is like our difference equations earlier, except that we go up to 3 powers of n instead of 2. Okay, well, what does that do for us? Well, we know that n cubed is equal to 0 cubed plus 1 cubed minus 0 cubed plus 2 cubed minus 1 cubed, all the way up to n cubed minus n minus 1 cubed. That is a telescoping series. Everything cancels out except the n cubed at the end. So now this means that n cubed is equal to 0 plus the summation is k goes from 1 to n of k cubed minus k minus 1 cubed. Okay, so, well, we can replace k cubed. We forget about the 0. And we replace k cubed minus k minus 1 cubed with its expansion, which is 3k squared minus 3k plus 1. And now we can separate those out into 3 different summations. And if you have a summation and every term is multiplied by the same number, you can pull that number out as a factor of all of the terms. Notice this second summation. We already know a formula for it, don't we? The last summation is easy to compute. It's just a bunch of ones added together. But when we look at this, we know this formula right here, so we can replace it. This is 3 times n times n plus 1 divided by 2. Now the only summation left is the sum of the first n squares, positive squares. So let's do some algebra. Actually, no, I'm gonna isolate this right here. Okay. Now we divide by 3. And if we want, we can factor the numerator. How does that numerator factor?
Bring the n out, so it will be 2n plus 2n squared plus 3n plus 1.
Does that factor?
No, you can divide it by 6.
2n squared plus 3n plus 1. How does that factor?
It's a quadratic sequence.
It's quadratic, but we can factor it into n plus 1 times 2n plus 1. Maybe later this week, we'll talk about factorization techniques. But there we have it. This right here is a formula for the sum of the first n positive squares. And we did it by constructing. We went 1 degree up with polynomials, and we constructed a series out of differences to intentionally untelescope n cubed into a bunch of quadratic terms. So we had degree 3 related as a sum of things of smaller degrees. And since we knew all of them except the one that we wanted, we were able to isolate the one that we wanted, the sum of the squares, and then find a closed form formula. And that's very nice.
I also found something for the triangular numbers. I found that for the first number is always 1, and for the second number you have to just keep adding 1 plus 1 plus 1.
That's
for
right.
the third number you have to keep adding 3. For the fourth number you have to add 6. For the fifth you have to add 10. For the sixth you have to add 15. For the seventh you have to add 21. For the eighth you have to add 28, and so on.
Good. And if you keep looking for patterns in this grid, you will find more and more patterns, and they may become more and more helpful. And it might be good to ask, why do these patterns exist? Can I come up with an algebraic explanation of all of them? And it will take some time to absorb, to get to the point where you can creatively use this type of algebra. But I did want to introduce it along with figure-eight numbers, because figure-eight numbers are, really, they're kind of simple. They just start with adding dots, right? We add but the level of algebra that we can develop to help handle them better is something that can be creatively used in a lot of different contexts. Let's call it a day. That was fun.
Mr. Crawford, just one quick question. So I wanted to be clear on the use of the sigma notation. So is it basically like you make a variable for the series, a variable that can represent the entire summation?
That's right. That's what we call the index variable. Let's see, did I write that somewhere? Yeah.
Yeah,
of course, you can use any variable you want. A lot of times you'll see I equals, or K equals, or J equals. But yeah, I chose K. And I said each term is going to be K, but we're going to replace it with 1, 2, 3, 4, 5, 6, all the way up to N. And so, the left-hand sides of these two equations are the same. One is just written in this compact notation. And you should find this notation in your AOPS books, The Art of Problem Solving, Volume 1. Am I correct in saying you all received a copy of that?
Yes.
You should find some more examples of sigma notation in there, and that'll give you some more practice with it. In fact,
thank you.
I'm going to encourage that as homework. Do that. Find the chapter with sigma notation and work a few problems in there. And any other questions?
Yes, for the rate, you said we should go and work some of the questions inside, but when I checked, they only had the answers without like the show working of them.
Right. I don't have full solutions to all of those, but do your best to craft your own solution. You can check your answers with mine. If there's a problem that is particularly tricky, post it on the message board and try to answer each other's questions on the message board. I'll come in and answer if one goes unanswered for a couple of days, but try to answer them. That'll give you practice putting the equations together nicely and communicating your solution.
Okay.
Any other questions? Okay, well, I'll see you all on Wednesday.
Okay.
Okay, thank you, Mr. Crawford.
Thank you, Mr. Crawford.
Thank you.